So remember, our goal is to try to get out of my haunted house, but the thing is we need to watch out for those trap edges. Remember, we cannot cross those edges that have traps on them, right? But we don't know where they are until we run into them. We're going to see that this actually plays a very interesting role with how well we can solve these problems, at least without any additional power, okay? So I'm going to define a couple key pieces of terminology to help us measure how good our approaches are. And you're going to find that a lot of the ideas we're going to have here are really going to be nice and simple to deploy. But I want to talk about measuring the quality of our answers. Measuring solution quality. So I'm going to introduce you to an important concept from online algorithms. So as an important remark, for the concepts we're going to talk about here, efficiency doesn't matter. It's actually about how well you can actually compute the solution. However, every algorithm I'm going to highlight here, all of them run in what we call polynomial time. So these are all going to be fast, efficient, but the thing is that that's not necessarily a part of this. The issue here is how much we know about potential choices in the future. And you're going to see how this is going to play out when we start actually digging into this. So what we called that over there, the Canadian traveler problem, is an example of an online problem. Like I told you, parts of the input are revealed as the algorithm processes the graph. So we're going to introduce this idea of competitiveness. So we're going to say, so I must stress that we call an algorithm online if it's attempting to solve an online problem like this. Namely, it is going to make choices depending on as the input comes in, okay? So that's my very simple way of describing it. I'm not going to be too formal about it here. However, this part I have to be formal. So an online algorithm is C competitive for an online minimization problem, like our problem. So we're trying to find the shortest path, not the longest path, right? An online minimization problem. I'm going to call that capital Pi. Hopefully I'm not making you hungry for pi. If for every instance x of pi, remember x is just the graph and of course our trap edges, and k. And I must stress there's a couple of things I want to point out, just as a matter of notation for this definition. We're going to define what's called opt of x. This is the optimum. So this is like the length of the shortest ST path if you knew where all the trap edges are. So this is what we call offline, meaning that you know all of the input in advance. So for that instance x. And likewise, I'm going to have the actual length of the path I get when I use my online algorithm. So this would be the value of the feasible solution. In that case, that would be a path that I get when I give x to the algorithm. So that being said, let me define what this is. If for every instance x of pi, it has to be that alg of x over opt of x, which I'll often write as just opt, is less than or equal to c. So it means that if you actually take this together, you'll notice that I'm allowed to, so I call it C competitive if whenever the algorithm gives me a solution, one. Now keep in mind, I'm using that word very loosely. I mean actually a feasible solution, one that follows the rules of the problem. May not be the actual shortest path, but it is in fact going to be always no worse than c times the value of the optimal. That's what this ratio means. You can just multiply both sides by opt of x, and you'd see that its alg x is less than or equal to c times opt of x. So it means it can be no further away than a multiplicative value of c away from the optimal. So for those that are familiar with the idea of an approximation algorithm, this is very similar to that. Except it's a little different, right? Because remember, the point here is that this optimum isn't without that knowledge. It is, in fact, when I have all of the input. Well, we call it the offline version. Just like I mentioned earlier, if I wanted to solve the offline version of the K Canadian Traveler problem, I could just use Dijkstra's algorithm because I know where all the trap edges are, right? I can just get rid of them and just run Dijkstra. But now this is going to be an important part for us. So just as an example, just to be very clear, if I give you a too competitive online algorithm, that means that the answers I get are always going to be within twice as bad as the optimal. So it's always going to be 2 times away from the value of the optimal. You're going to see that's not going to be very optimistic for us in this scenario, but most certainly that's something that you can look for. So like I mentioned, we're not going to care, in this definition, we're not going to talk about efficiency at all. If we're talking about approximation algorithms in contrast, their efficiency matters. Very often, like if I gave you what was called a K approximation algorithm, in that case, it would be that it has to be, requires that it runs in polynomial time. Here, we're not going to care about that. But it's a desirable characteristic for an online algorithm to run in polynomial time at most. Okay? So that's the Canadian Traveler problem. We would like to get it so that this competitive, this C competitiveness, I want to make this C as small as possible. I want to get it close to 1 as possible, right? Because if it's 1, that means that this ratio is no more than 1, meaning that it has to be the optimal answer every single time, right? But I must stress that if you're wondering what in the literature what this is called, this C is called the competitive ratio. This is called the competitive ratio. So they call it competitive factor as well, but usually competitive ratio because of this definition. So are there any questions at all before we actually get into now some juiciness? Because we're going to start talking about algorithms now. So what I was thinking of doing is we're going to try starting off with our first strategy, policy, our first online algorithm for trying to attempt to solve the K Canadian Traveler problem, how to escape our haunted house. Is everybody excited?